Hi everyone, in today's video we're going to talk about making parallel vision transformer in JAX using device mesh. So let's get started. In this experiment I used 3 options to train the parallel vision transformer, and one of the options throw out of memory error. I'll talk in this in details, but first let's have a look at the code. Before I jump into the code, I want to acknowledge the help of this source, train a mini GPT language model with JAX. So I borrowed some code from this web page where they explained how to use a parallel model device mesh in JAX to train a mini GPT model. So this is my code. I'm using Kaggle notebooks. Here I'm importing libraries. Here I'm setting the data configuration file and the model configuration file. And these 2 helper functions will help me convert the images in CFA10 into NumPy arrays, so to make them compatible with JAX. Here I'm importing CFA10 from TorchVision, and I'm using a data loader using grain data loader. I used to use Torch data loaders, but in this source train mini GPT they are using grain. So here they are loading the data. First they are using a sampler over the dataset, then they are using a data loader from grain library. It's basically the same thing. It's an iteratable data structure. You want just to pull out the image and its labels and start training. Before, JAX doesn't have a train loader. I had to use Torch, and I was afraid of compatibility between JAX and Torch. Now this one is just specifically designed for JAX and flax. And here in this cell I'm just plotting some images from the trained data loader, and this is where I'm setting the device mesh. So the 3 options I'm using in this blog post, I'm using 4x2 device mesh, 8x1 device mesh, and no mesh at all. So I'm just passing the images into the model. I'm not designing a device mesh, and I'm not defining parallelism, because I want to see how JAX will react if I don't set any parallelism options. So why 4x2 or 8x1? Because in Kaggle notebooks the accelerators are TPU VM v3.8. Each TPU has 8 devices, and in this notebook I'm running on 8 core devices onto a TPU. If I print out JAX.devices, it will print 8 devices and the coordinates of these 8 devices. So the mesh dimensions has to match the number of devices. So I'm setting the batch and model. I'm splitting the batches over 4 devices, and I'm splitting the model over 2 devices, or I'm splitting the batch over 8 devices and I'm keeping the model. So this is equivalent of just 8 and a comma. You don't set the options for the model. Here is the definition for a VisionTransformer class. It calls a patch embedding, which is basically a convolutional layer that cuts the image into patches and maps them into the embedding dimension, and an encoder block, which is basically an attention block followed by MLP. All these classes will be wrapped into one vision transformer. I'm running these images through the vision transformer. Notice here in kernel initialization and bias initialization, I'm calling NNX with partitioning, which is the same thing they have done in the mini GPT. So if you search with NNX with partitioning, this is basically we are trying to replicate the model parameters over the partitions that I'm not using the partitions. We are trying to replicate the model parameters over the device mesh that we are creating. Remember that we are using 2 configurations. The first configuration is 4x2, and the second configuration is a first configuration we are doing data parallelism and model parallelism, but in the second configuration we are only using data parallelism. There is a difference between how the train mini GPT example defines the flax with partitioning and an example in flax. So here in flax they are using NNX with partitioning and they are calling the initialization function, but in train GPT they called the uniform initializer and they are passing the name sharding. But here they are not passing the name sharding, they are passing 2 options, and when they call that layer, they pass the sharding. So these are 2 different ways to use NNX with partitioning, and this is scale-up example in flax, and this is a train mini GPT example in JAX AI stack. So this was the vision transformer architecture. I just want to say that this model is not optimized to reduce the loss or improve the accuracy on CFR10. The sole purpose of this architecture is just to measure the memory and running time for 3 different parallelism configurations. Here I'm defining the model, and this is the loss function, and this is the train step. This is the training loop, and I'm setting a JAX.profiler, and here I'm stopping the profiler. To visualize how parallelism is performed in JAX, there is a great method here. It's called visualize array sharding. So here I'm pulling the encoder block, the first encoder block, I'm pulling the MLP and fully connected layer, and I'm pulling the weights and visualize the sharding So this is the configuration when I'm setting the batch 4 and model 2. The same copy will go to TPU 0, 2, 4, 6, and another copy will go to 1, 3, 5, 7. And it's JAX job to accumulate these model parameters. And the same thing goes for the bias. Now, if I visualize the labels, which is sharded across the data dimension, across the batch dimension, labels will be split across these different devices. But when I set the mesh to be 8 by 1, this won't have an effect on the model because the model will be copied over all devices. It will affect how the data is split. Instead of splitting the data into 4 groups, it will be split into 8 groups, and each group will be assigned to a single device on a TPU. To check even more that our parallelism is working as expected, let's check the HLO commands. So if I go to this configuration where we use the batch size 1024, so I go to HLO op stats and I search for 32, 32, 3. This is the size of the CFA10 images. I can see that the whole batch was set into one device. So 1024 by 32 by 32, this is the first convolution layer, the convolution layer that splits the images into patches. Now let's check how this is done in 4 by 2 configuration and 8 by 1 configuration. So in 4 by 2 configuration, so this text that we searched for returned 256 by 32 by 32 by 3. So this is the first convolution layer. If we divide to 1024 by 4, this is 256. So each device will handle 256 images instead of 1024, which is the original batch size that we are passing to the model. And in 8 by 1 configuration, this text here returned 128 by 32 by 32 by 3. So 1024 divided by 8, this is 128. And this means that each device is getting 128 by 32 by 32 by 3 for the first convolutional layer. That is the first part of the VisionTransformer. So this is another way to check that the parallelism is done right, because these are the low-level commands for each device. Just to visualize the batches, so the train loader in CFA10 will have 50,000 images. So these are the images. It's 32 by 32 by 3. If we set the batch size to be 128, we will have 390 full batches, and we will discard the last one. So in 4 by 2 configuration, this batch will be split into 4. In 8 by 1 configuration, this batch will be split into 8. If the batch size is 1024, we will have 48 full batches, and we will discard the last batch. Again, the same thing. In 4 by 2 configuration, this will be split into 4 groups. In 8 by 1 configuration, this will be split into 8 groups. If the batch size is 4096, we will have 12 full batches, and we will discard the last one. It will be split into 4 groups in 4 by 2 configuration, and it will be split into 8 groups in 8 by 1 configuration. To run these parallelism configurations, I have this 4 by 2 option and 8 by 1 option, and I have another notebook where these are turned off and NNX with partitioning is turned off. Also, one more thing, I just remembered, you don't use JAX device put. So you just pass images equals batch 0 and labels equals batch 1. So in the other notebook, I'm just turning off parallelism and metering the running time and memory consumption. So at the end of the experiment, I got these numbers. So the slowest was 8 by 1 configuration. This is expected because the accumulation is not done in 4 groups. It's done by 8 groups. So there is an communication overhead. But the surprise was when I'm not using the mesh, this was the fastest because there is no communication overhead. And until I used the batch size 4096 and I got out of memory error. And the peak memory allocation, the 8 by 1 option was the most efficient. It didn't use much memory, but also I can run 4096 batch size on this configuration, but I cannot run it without a mesh. So let's check what's actually happening in TensorBoard. So I'll explain at the end of the video, I'll explain how to install TensorBoard, but now let's check. Here I have 8 configurations, the 8 by 1 mesh with 4096 batch size, 128 batch size, 1024 batch size, and the same thing with 44 by 2 mesh. And with no mesh, I only have a batch size of 128 and 1024. If we go to this configuration, 8 by 1 batch size 4096, this is the overview page. This is the time. And if we go to memory viewer, the peak memory allocation was 4300. In 4 by 2 configuration, it has to be double that. So let's go and check that. So it's 8500. Now, if I go here to overview page, I would see that the number of device cores is 8. And if I go to memory profile, I can see all 8 devices and how much they are using. But here is the surprise. If I go to the profile where I didn't use any mesh for parallelism, the number of device cores is 1. So it's not utilizing the whole devices on the CPU. It's not utilizing the whole 8 devices. It's only using one device. And I can confirm that from the memory profile. Here it's only 1. So that's why it threw out of memory error, because JAX was trying to put the whole batch into a single device. So that was surprising for me, because I started thinking of all my JAX projects I did before, because I wasn't using this option, JAX.device put, and I'm not using a device mesh. So is JAX only using one device by default, and you have to instruct it to use a device mesh, and you have to put your tensor into a JAX.put device? But this is extremely important after what I run through, not using all devices. At the end of the post, I put the commands that I used to run TensorBoard locally, because I didn't use TensorBoard on Kaggle. I find it very painful to run TensorBoard on Kaggle or Colab, and I was afraid of losing the profiling files. Just randomly restarting the environment in Colab on Kaggle will lead into losing my files. So what I have done, I just profile one epoch, then it will appear here in the output. You will see something similar to this hierarchy: JAX profile logs, plugins, profile, timestamp, and you will find that JSON file. For this one, I got 1 gig, sometimes 1 gig, 1.5, but for this one was very light. So I downloaded these 2 files, and I tried to do the same hierarchy in my downloads folder. So I'm doing downloads, plugins, profile. This folder name will appear in TensorBoard here, and I put the JSON and explain files into this folder, and TensorBoard will pull them from there. And to install TensorBoard, I'm just using Conda environment for TensorBoard, and just installing TensorBoard, then I'm running this command here. It is very useful to inspect, and that's how I found out that if I don't use any mesh, I'm just running one TPU device. That's it, guys, for today's video. I hope it was helpful. I'll put all the commands and screenshots in one blog post and share it with you guys in the description below. Thanks for watching. Bye.